Okay, we're going to start in Chapter 1 with a review of general chemistry and some of the topics that we're going to be using in organic chemistry. And what we're going to do is we're going to talk about the general chemistry topics in the context of how we're going to use them within organic chemistry. And so let's start with the idea of bonding. So if we're looking at bonding, there are two types of bonds that we can form, and that's going to be ionic and covalent bonding. So just as a review, remember ionic bonding is when we have a cation and an anion that are electrostatically attracted to each other. The electrostatic attraction between the positive and negative charges is based on, number one, the distance between them and the size of the charge. Now, the way that we get a cation and an anion is that there is a metal, let's say, that has a valence electron. Maybe there is another atom that would like that valence electron, and so the metal will transfer that electron, losing to become a cation, and then the other atom gaining an electron to get the negative charge. So the idea here is that when we form an ionic bond, number one, the ionic bond is formed between ions, and it involves a complete transfer of an electron from one species to another. Now, also remember from general chemistry that an atom's ability to attract electrons or electron density to itself is what we would then call electronegativity. So when we form an ionic bond, we're going to do so with atoms or elements that are basically electropositive, meaning that they like to give up their electrons, and atoms that are highly electronegative that are going to want that electron. So my general rule is, if I'm looking over here at the periodic table, if I take something from the extreme left-hand part of the periodic table, which is where your metals are, and I combine them with something on the extreme right-hand side of the periodic table, and this block of elements from boron all the way over to the halogens, that block is what I call the main group elements. But if we take something from the far left-hand side and something from the far right-hand side and we bring them together, we're going to get transfer of the electron and the formation of an ionic bond. Simplest case would be if I took sodium metal and I reacted it with a chlorine atom. The sodium would give up its electron to the chlorine. We would end up with a sodium plus, and then our chlorine becoming a chloride ion, and so we would make NaCl, which is a good example of an ionic compound. So that's how we would form an ionic bond. And to be honest, in organic chemistry, it'll be second semester when we start talking a lot about ionic bonds within organic chemistry, because organic chemistry is mostly based upon covalent bonding. So covalent bonds are ones that involve an element of sharing electrons, sharing electron density. And in general, covalent bonds are formed between the elements that are in the main group. And also over here, hydrogen. Hydrogen should basically go into the main group as well. So when we take main group elements, we are going to be forming then covalent bonds. And in this case, the electronegativities between the elements is not extreme. And we should take a step back here at this point and talk about electronegativity as a number. And I'm not going to get into necessarily a mathematical description, but remember on the periodic table that fluorine is the most electronegative element on the periodic table. And what that means is that as you go from left to right, you're going to be increasing electronegativity. And as you go up the periodic table, you also then increase electronegativity. So everything moves towards fluorine. And elements that are on the left-hand side of the periodic table have very low electronegativities. Elements on the right-hand side have very high electronegativities. So you get ionic bonding when you take something with a low electronegativity, something with a high electronegativity, and then that causes the electron to transfer. If we took, for instance, a carbon and an oxygen atom, or carbon and a hydrogen atom, what we end up doing is sharing electrons. And we should also invoke at this point, remember that when we're talking about covalent bonds, we're talking about having each element obey the octet rule. And remember, the octet rule says that we should be sharing 8 electrons, sharing or outright ownership of the electrons in order to form the most stable molecule and the most stable bonds. So for instance, if I had a carbon with its 4 valence electrons, and we'll talk about drawing Lewis-Strauss structures in a moment, but if I did that, then my hydrogens, atoms, would be sharing their electrons, and maybe I bring in an oxygen at this point. So oxygen, as we'll find out, has 6 valence electrons, and maybe put another hydrogen here. So the idea of covalent bonds is that we have basically a nearly identical electronegativities between the elements. And we're also then sharing electrons in order to get to the octet rule. So for instance, in this molecule, which is methanol, methyl alcohol, the carbon will be sharing electrons with the hydrogens, and it will also be sharing electrons with the oxygen. The oxygen will be sharing its electrons. It's going to own these 4 outright, which we'll talk about it in a few minutes, but it's sharing its electrons with carbon and hydrogen, so that the exception to the octet rule, the first exception, is hydrogen. Hydrogen will only share 2 electrons, but in this case, oxygen now is basically owning and sharing 2, 4, 6, 8, and the carbon is also then sharing 2, 4, 6, 8 to get to the octet rule. So we have this sharing, and the carbon hydrogen, carbon oxygen, and oxygen hydrogen would be covalent bonds. Now also remember from general chemistry that in this sharing doesn't have to be identically perfect. It doesn't have to be a perfect sharing of the electron density with the between the elements. That will depend on the electronegativity difference between the carbon and the other elements. So for instance, an electronegativity of hydrogen is, according to your textbook, 2.2 Pauling units. A carbon is 2.55, and an oxygen is 3.44. And so the electronegativity difference between a carbon and a hydrogen is slight. There's a slight difference. And we would call the carbon-hydrogen bond then basically a non-polar covalent bond. And what I mean by that is it's a nonpolar covalent bond simply because it is near perfect sharing. The electronegativity difference isn't that much different, and so in essence these carbon and hydrogens are sharing nearly equally those electrons. So nonpolar covalent is when you have a small electronegativity difference. On the other hand, as the electronegativity difference gets larger and larger, you can have the carbon-oxygen bond, which we would classify as a polar covalent bond. And the polar covalent bond then is one where we have, in essence, a larger electronegativity difference, but also it means that there is unequal sharing. And so in this case, the oxygen with the larger electronegativity value would attract the electrons away from the carbon a little bit more of the time. As we'll see as we work through and review, that oxygen, since it has more of the electron density in the bond, we could label it as a delta minus, because what it has is it has more electron density. And the carbon then, from its interaction with its covalent bond with oxygen, it would have a slightly positive charge because it's less electronegative and losing some of its electron density to the oxygen. The thing we should say at this point is covalent ionic bonding, polar covalent versus nonpolar covalent bonds, this is all a continuum of bonding. And so there's no real definitive boundary between nonpolar covalent bonds and the polar covalent bonds. And so in organic chemistry, since we're interested in looking at carbon, hydrogen, oxygen, we will look at nitrogen, the halogens, sulfur, phosphorus. Since we're looking at main group elements, we're either going to be looking at polar covalent or nonpolar covalent bonds. And it's relatively easy to make sort of a definition here of polar covalent versus nonpolar covalent. So let me go to the next slide and kind of give you a qualitative rule that we're going to use. And that is that if we have what I would call a perfect covalent bond, meaning that we have perfect sharing, equal sharing between the elements, we're going to have a true covalent, perfect covalent bond when we have two elements that are the same. So when we have the same elements attached to each other, there's no electronegativity difference. That's a perfect covalent bond. If we have a carbon-hydrogen bond, then we're going to treat that as basically a nonpolar covalent bond. And we're going to treat it almost as if there is perfect sharing. Although we won't on occasion. And from what we saw with the electronegativity numbers, the carbon would have a slight negative charge and the hydrogen would have a slight positive charge. But for the most part, we're going to treat this as if it was a nonpolar covalent bond, treat it as if there was basically equal sharing. When we have two elements that are different, like carbon-oxygen, or carbon and a halogen, or carbon-nitrogen, or even carbon-sulfur, all of these we're going to treat as polar covalent bonds. And as polar covalent bonds, the atom that's attached to carbon will be slightly negative, and the carbon itself will be slightly positive. So in this continuum of the covalent sharing, these are all bonds where there's shared electrons to form the octet rule, but this is how we're going to classify them, as either a perfect covalent bond where there is no charge differential, or a basically nonpolar covalent bond, or the polar covalent bonds. And we'll use those later as we talk about polarity of molecules. Okay. So the next thing that we need to do is in order to look at these bond differences in terms of their covalent nature, we need to be able to draw Lewis dot structures. And so here's a quick review of the rules or steps for drawing Lewis dot structures. First, you have to identify how the atoms are attached. At the current time, there will be no rings, and we'll get to rings later. And typically what I do is I give you sort of the skeleton structure, and then you have to figure out how to fill in the atoms, or fill in the electrons. Hydrogens and fluorine atoms typically are at the end of the molecule, and the central atom is typically the least electronegative. There are some exceptions. When a halogen is attached to oxygen, it is, although it's the most electronegative, it is the central atom. What we're going to do is write Lewis dots around each atom in the structure from the periodic table. We're going to need to know how many valence electrons it has, and then we're going to form single bonds. If it's an ion, we'll add in the appropriate number of electrons or take them away, and then we'll pair up the electrons to form double and triple bonds, trying to form as many octets as we can. So you can use those rules as we go through, and we'll do some examples, and I'll ask you to draw a couple of examples as well. So remember, on the periodic table, the number of valence electrons. So if we're talking about the valence electrons, the number of valence electrons for each element is given by its column number. So over here, this is 1 valence electron. Then we won't do much this semester with alkyl metals, but they would have basically 2 valence electrons. Boron would have 3, carbon would have 4, nitrogen 5, oxygen 6, halogen 7, and 8 for the noble gases. So we need a periodic table in order to determine the number of valence electrons. The formal charges, let's come back to this formula. Let's write a couple of Lewis dot structures here to get ourselves back into general chemistry rhythm, and then we'll figure out the formal charges. And then we'll talk about resonance. So here's our first example. Let's draw the Lewis dot structure of HNO3 nitric acid. Nitrogen is the center atom. What I would tell you in this structure is we have a nitrogen. We have 1, 2, 3 oxygens attached to that nitrogen, and then we have a hydrogen attached to one of the oxygens. So in terms of writing this structure, number 1, it has no overall charge. And so what I would do is, the way I like to do this, and you may have a different system. If you do, one of the rules that I've learned early on is don't mess with student systems. So I'm not going to change your system. I'm just going to show you what mine is. What I like to do is go through each element and add in the number of valence electrons to give that atom if it was a neutral charge. So for oxygen, we would have 1, 2, 3, 4, 5, 6 valence electrons, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and 6. For nitrogen, if we go back in the periodic table, nitrogen is in column 5, and so nitrogen would have 1, 2, 3, 4, 5. And notice that what I'm doing is I'm writing the unpaired electron sort of in drawing it where there's another atom that will eventually form a single bond. Now this is a neutral molecule, so I do not have to add or subtract any electrons, so we'll just leave it as is. And now what we would do is now we're going to go ahead and form single bonds. So we're going to have elements share electrons. Remember, the ultimate goal here is to form octets. So I would share these 2 electrons for nitrogen and oxygen, and these 2. And I forgot my hydrogen over here. It has one valence electron. I would share the oxygen. So we're going to pair up the unpaired electrons to form these single bonds. And now I'm going to go element by element and see if it has an octet. Hydrogen, of course, is an exception to the octet rule. It can only have two, so it's sharing two. It owns one. Oxygen owns one. They both share that pair of electrons in that bond. Oxygen over here has 2, 4, 6, 8 electrons, so it's at its octet. Nitrogen over here has 2, 4, 6, 8, and so it has an octet, but these two oxygens with their unpaired electrons are only owning and sharing 7. And so what we need to do is we need to somehow get these oxygens to an octet. Now, remember that the octet rule you cannot break. So for elements, and go back to the periodic table here, elements that are in row 2 or higher must obey the octet rule. 10 electrons to carbon is an unforgivable error. Carbon cannot form an expanded octet, neither can nitrogen, neither can oxygen, neither can fluorine. Now, if you're in row 3 or lower, then you can form an expanded octet. And we'll talk about the reasoning for that a little bit later on if you don't remember from general chemistry, or if that was not talked about in your general chemistry class. So all of the atoms that we have in this molecule are row 2 or higher, so therefore we cannot violate the octet rule. So here's what we'll do. What we'll do is we will take and pick up this electron, and I will move it up here. So I'm going to take that electron, I'm going to give it to that oxygen, and I'm going to get my eraser here, and I'm going to erase that one. Can I do that? Absolutely. Why? Well, because I'm in charge. I can do what I want. But it goes beyond that, right? When we're writing in the valence electrons in a molecule, basically we're just accounting for the total number. We could distribute them any way possible as long as we don't violate the octet rule. So picking up an electron from one atom and moving it to the other is perfectly fine. Now, that gives this oxygen an octet, so it's okay. But now this oxygen has 2, 4, 6. How about I take this pair of electrons on the nitrogen and I use it to form a double bond? And so if I do that, I think I now have all of my atoms having octets, except hydrogen. So if you remember, these are the kinds of maneuvers that we make, and that is going to allow us to draw a successful Lewis dot structure. So I think I have one here. Now, the next thing to do once you've drawn the Lewis dot structure and all of these elements have octets is to calculate the formal charges on each atom. The formal charges all must add up to the formal charge on the original molecule, which in this case is 0. So let's go back. How do we draw formal charge, or how would we calculate formal charges? Well, there's a formula. The formal charge is the number of electrons in the neutral atom minus 1/2 the number of bonding electrons minus the number of unpaired electrons. So let's do that for this oxygen over here. So oxygen came with 6 valence electrons in a neutral oxygen atom, and right now it is sharing 4, and it owns these 4 outright. So this is 1/2 the number of bonding electrons, and this is the number of lone pairs, lone pair electrons. So in this case, 6 minus 2 minus 4 is 0. Now, that formula will always work, but here's another way to think about this, and that's part of my job is to give you different ways to think about it, and part of your job then is to figure out what works for you. So in this case, what I like to do is I like to say this oxygen came with 6 valence electrons. How many does it now own? Now, ownership is different than sharing. This oxygen owns these 4 outright. And it owns 1 of the electrons in each of these 2 bonds. It shares a total of 4, 2 with nitrogen, 2 with hydrogen, but it owns 1 outright. So if this oxygen and this hydrogen were to amicably separate, each atom would get its electron back. So in this case, that oxygen owns 4 outright, and it owns 1 in each of the bonds. So it owns 6. It came with 6. There's no net change. 0 formal charge. Okay, so that's another way of looking at formal charge. Number that it came with minus the number that it owns. So let's calculate the formal charge on this oxygen. As a matter of fact, the video is going to stop right now, and you're going to be asked to type in the formal charge of that oxygen. And then, and when it does this, I'm grading these on participation. I'm able to go back and look and see if there's if as a class we missed a problem. So when I say we're going to stop and the video stops, it's going to come up with a quiz. You're going to go ahead and type in an answer, and then we'll see whether you're correct or not as we continue the video. Okay, you're back. So what is the formal charge on this oxygen? Well, this oxygen came with 6. It owns 2, 4, 6, and it owns 1 of the 2 with the nitrogen. So 6 minus 7 means it has a -1 formal charge. How about this nitrogen? What is its formal charge? The video is going to stop again and type in the number. Okay, you're back. What's the formal charge on this nitrogen? That nitrogen came with 5 valence electrons. It owns 1, 2, 3, 4. It has a +1 formal charge. And finally, this oxygen, what's its formal charge? Okay, you're back. It owns 2, 4, and it shares, but owns another 5, 6. Came with 6, owns 6, owns these 4 outright, owns 1 in each of the 2 bonds. It has a 0 formal charge. Okay. So that is how we do the formal charges and drawing the Lewis dot structures. Now, for those of you who were looking at this saying, are there other legitimate, correct Lewis dot structures that I could write for this HNO3 molecule? The answer is yes, and that will lead us into the idea of resonance structures, which we will also be reviewing. Okay. Okay, let's look at PO4 3- as an example of how do we handle an atom or a molecule that has negative charges. So I'm going to, first of all, I'll give you the structure, which is a P with 4 O's. Oxygen will have 6 valence electrons, so I'm going to write this as 2, 4, 5, 6, 2, 4, 5, 6, 2, 4, 5, 6, 2, 4, 5, 6. And phosphorus is right under nitrogen on the periodic table, so it has 5. So I'm going to say 1, 2, 3, 4, and 5. Now, I've got a -3 charge, which means I have to add in 3 electrons. And where can I add those? Anywhere. Really? You can add them anywhere? Yeah. Remember, this is an accounting game with electrons. In the end, we'll know whether we've accounted properly by whether or not the octet rule is, not violated. So in this case, let me add one here, let me add one here, and let me add one down here. So now I have an overall a 3- charge. Now let's form single bonds. So I'm going to form a single bond here and here, here and here, here and here. Uh-oh. Let's just take one of the two here and form that single bond, which I don't like. Okay. So now I've formed the single bond. So now what I want to do is form double bonds in order to make sure everything has a full octet. So if I start with this oxygen up here, it has a full octet. This oxygen down here does not. This oxygen over here does have a full octet. It's okay. And this oxygen over here has 2, 4, 6, 8. It also has a full octet. And I'm going to rearrange the electrons so it looks normal, or it looks reasonable. So let me rewrite that structure. So the oxygen over here has 3 with this electron right here. Maybe I move it to that position. Then the phosphorus still has 1 unpaired. This oxygen up here has 3 lone pairs. This oxygen over here has 3 lone pairs, and down here, this is where you can make a mistake. Sometimes I will do this and I'll say, I'm showing you what kinds of mistakes you can make. And of course, I'm just making that mistake myself. Okay, you want to make sure as you rewrite the structure you don't gain or lose electrons, because then in the end you will get the wrong answer. Okay, so now what I have is I have 1, 2, 3 of the oxygens all have octets. This phosphorus right now is sitting at 2, 4, 6, 8, 9. Phosphorus wrote 3 or lower, so it could have an expanded octet, but it's not going to in this case. So this oxygen over here needs an electron. This phosphorus really can give up. So I'm going to take this electron and just give it to the oxygen. Again, can I do that? As long as I don't lose it along the way, and in the end, if I don't violate the octet rule. So here's my final structure. There we go. Okay. So now let's go ahead and check atoms. Do they all have octets? Yes, they all have octets. They all are a combination of owning and sharing 8 valence electrons. Now, formal charges. Okay, again, the video is going to stop. So the first thing I would like you to do is, number 1 here, what is the formal charge? And notice all the oxygens are the same. So what is the formal charge on the oxygen? Okay, you're back. What is the formal charge on the oxygen? Well, that oxygen, any of these oxygens owns 2, 4, 6, 8, 9. Sorry. Yeah. Sorry. 2, 4, 6, 8, 9. That violates the octet rule. 2, 4, 6, 7. Came with 6. Now owns 7 minus 1. So the formal charge on oxygen is minus 1. Okay, question number 2 then is, what's the formal charge on the phosphorus? So what is the formal charge of the P? Okay, you're back. The formal charge on the P, the phosphorus owns 1 in each of its 4 covalent bonds. 1, 2, 3, 4. It owns 4. Phosphorus came with 5. It owns 4. That means it has a +1 charge. Okay. Now, as the final double check, no atoms here violate the octet rule. They all have filled octets, which is good. And now the final test, and if your structure fails this test, it is wrong. Let's add up all the formal charges and make sure that they add up to this -3 overall. So each one of the oxygens was -1. That's -4 total, but the phosphorus is +1, so therefore the net charge is -3. So more than likely when it passes that test, you are correct. You have the correct structure. I can guarantee you 100% of the time, if it fails that test, you have the wrong structure. Okay, so that's kind of a refresher on how to draw Lewis dot structures for HNO3 and PO4 3-. Okay, NO2-, I'm going to leave that for you to try as a practice problem, and I will post that answer in the discussion board. Actually, I think is where I will post it, so that way you can take a look at it, because I don't want to gum up the works on the modules. So I'll post that in the discussion board. And OCN- is going to be our next molecule that we're going to look at. Okay, so OCN-. OCN-, I've given it to you with an O, a C, and an N. And so what I would like you to do in this case is let's draw the Lewis dot structure for OCN-. I'm going to say this a lot in this class. If you're an overly ambitious go-getter student and you know who you are, then you could stop the video right now and go ahead and draw the structure out and then come back and see if you were right. If you're still kind of, I need another example, then let's have the other example. So in this case, oxygen would have 2, 4, 5, 6. Carbon has 4 valence electrons, and nitrogen has 5 valence electrons. So that's our first step. Draw out the number of valence electrons in each of the atoms. Now, next thing I want to do is I need to add in 1 electron to make this a negative charge. Where can I add that? Anywhere. Let's add it to the oxygen. Could you add it to the nitrogen? Sure. Could you add it to the carbon? Sure. I wouldn't, but you know, usually we try and add it to pair something up. So now I'm okay because now I've given it an extra electron. It's now got a negative charge. So now let's go ahead and let's form single bonds. Oxygen to carbon, carbon to nitrogen. Great. Okay. So now my oxygen is perfectly fine. It has an octet. My carbon, it's going to need to share some electrons in order to form an octet. So how about we share the carbon and nitrogen unpaired electrons there. That would give this carbon 2, 4, 6, 7. Nitrogen would have 2, 4, 6, 7. Let's just pair up these two unpaired electrons, and now we will get, everybody will be happy with an octet. We'll have a triple bond between the carbon and nitrogen, and that nitrogen will have a lone pair. The oxygen has 3 lone pairs. Okay, so that's one valid Lewis dot structure. Are there others? Sure. We could start out here, and I'll kind of go from the beginning, and then I'll show you how when you draw one Lewis dot structure, you can get the others. But let's say that I went back to my original structure here. And I know I'm kind of cutting some corners here because I'm going to put the single bonds already in. Now, I'm at the stage where I need to add that 1 electron. Let's add that one extra electron there. Okay, now let's go ahead and share things. How about I share this pair of electrons between the carbon and oxygen, and let me share this carbon-nitrogen unpaired electron to form my octets. So I could write a Lewis dot structure where there's a double bond between oxygen and carbon and between carbon and nitrogen. And then the oxygens and nitrogen would have 2 lone pairs each. Is that a valid Lewis dot structure? Absolutely. And let me go back to the beginning here. And let's draw a third. So now I'll go and just put the unpaired electrons back in. Okay, there is my neutral molecule. I need to add, again, this 1 electron. So let me add it to this nitrogen over here again. Now let's share to form the single bonds. And now let me do the following. Let me share this pair of electrons to form the carbon-oxygen double bond. But now let me pick up this electron and give it to this nitrogen so that I have this, which then I can share those 2 unpaired electrons and form my third resonance, or third structure, which I'm going to call resonance structure. But you probably already knew that. Okay. So there's my third possible Lewis dot structure. So for this molecule, there are 3 possible Lewis dot structures for this molecule. And the question is, which one is correct? And the answer is none of them. Well, all 3 of them are correct. I should have asked a different question. Which one of these 3 is the true structure? And the answer is none of them. Okay. What I now have formed are what are called resonance structures. And the question is, what is a resonance structure? A resonance structures are these representations that differ by the placement of 2 things. They differ by the placement of lone pairs. So the difference is in the lone pairs, and it's also different in the multiple bonds. So each one of these 3 structures has different numbers of lone pairs and different numbers of multiple bonds. And so those are resonance structures. So resonance structures are represented by a double-headed arrow. And let's go back and let's talk a little bit about the rules of resonance in terms of looking at these structures. So here are the rules of resonance. First of all, resonance structures, as I've defined them, they differ from each other only in the placement of their pi, which means they're multiple bonds, and their non-bonding electrons, which means lone pairs. Number one, resonance structures are imaginary. They're not real. The true structure is what we call the resonance hybrid, and we're going to write the resonance hybrid for that molecule the ion that we just drew. Resonance forms are basically, let's say that I can use the idea of resonance theory like I would genetics. So my best example of resonance forms would be, let's say that you bred a pit bull and a chihuahua. The offspring of that would be, would not constantly be flipping back and forth between a pit bull and a chihuahua. I mean, that'd be cool to see, but that's not what happens, right? It's some mixture of the two. And in chemistry, that's what hybrid means. Hybrid means that we have a mixture. And as in genetics, they don't necessarily mix 50-50. So the resonance hybrid is going to be some mixture of those resonance structures, those resonance forms. But some resonance forms will be contributing more, and some will be contributing less to the resulting hybrid. So the hybrid will look more like one and less like the other. Right? I mean, you can apply that to any principle that really involves genetics. People, chihuahuas, the whole, any of those. And the whole pit bull chihuahua thing, actually, if you want to search on YouTube, there was a Super Bowl commercial where they showed the Labrador Hua, I think they called it. It was a chihuahua body with a Labrador head on it that went around chasing cars. And I swear they stole that idea from me, because I've been using the pit bull chihuahua analogy for the better part of 20 years. So we'll talk about the resonance hybrid, how to draw it, and our next step is actually to evaluate the resonance structures. So my digression is over. All resonance structures have to obey the normal rules of valency. You cannot have an expanded octet in a resonance structure for things that cannot form expanded octets. Carbon, nitrogen, oxygen cannot form expanded octets. The resonance hybrid is going to be the most stable structure, and it's more stable than any of the single resonance forms, which is why the resonance hybrid is the true structure. Okay, let's go back. Let's go back to our original molecule. Okay, now, first thing we need to do for these three resonance structures is we need to assign formal charges. So, again, the tape's going to, I always say the tape because I'm old. The video is going to start and stop, so question number 1 is going to be, what is the formal charge on that oxygen? If you said -1, you are correct. What is the formal charge on that carbon? If you said 0, it is correct. What is the formal charge on this nitrogen? If you said 0, you are correct. Let's do these three. What's the formal charge on this oxygen? If you said 0, you are correct. Formal charge on this carbon? If you said 0, you are correct. Final, this nitrogen. Formal charge is -1. All right, last three. This oxygen, what's its formal charge? If you said +1, you are correct. Carbon, zero. This nitrogen over here, if you said -2, you are correct. So those are our formal charges. Okay, hopefully everybody got all those right. So now let's go through and let's determine the stabilities, the relative stabilities of each of these resonance structures. Because in the rules of resonance, the different resonance forms don't have to be equivalent in energy. So one may be more stable and the other one's less stable. So now what we need rules to figure out which one is more or less stable. So let's talk about the stability of resonance contributors. So there are three rules. We look at number one if there's a tie, or I should say we look at number one if that tells us that one is more stable than another. That's great. If there are ties, we go to 2. If that breaks the tie, great. If not, we go to 3 as our tiebreaker. So these are sequential rules in order of importance. So first of all, each atom should have a completed octet. Let's go back to our structures here. Do all of these resonance structures have octets? Yes, they do. Okay? And to be honest with you, I always ask you to write the resonance structures that have completed octets. Why? Because those are always going to be the most stable resonance structures. So in general, that will be a given. That rule number one will not break any ties. So now we go to number 2. Structures should have 0 formal charges. That would be best. Or small, meaning ±1 is better than ±2. Not only are we talking about the value here of the formal charge, small better than large, but we're also looking at the number of charges here. So the number of charges, a +1, -1 versus maybe just a -1. Now, you can't have that because they all have to have the same overall charge. But let's go back and take a look at the structure here. So are there any here that we can clearly say are more or less stable than the others? I would say number C here, and now I should put in letters A, B, and C. And so number C here has a +1 and a -2. That's going to clearly be the least stable. Why? Because it basically fails rule number 2, which says we want small charges. For A, we have 1 -1 charge. For B, we have 1 -1 charge. So as far as rule number 2 goes, A and B are tied, but C clearly less stable. Okay, so we've got the least stable. So now we have to break the tie between A and B. So now we go to rule number 3. And rule number 3 says that the formal charges should agree with electronegativity. What exactly does that mean? What that means is this. When I have a negative charge, I would like that to go with the most electronegative element. And when I have a positive charge, I would like that to go with the least electronegative element. Okay. So that means we need to know what the electronegativities are because the difference between A and B here is that in A, it's the oxygen with the -1 charge, and in B, it's the nitrogen with the -1 charge. Now, let me draw out a real quick periodic table. C, N, O, F. Everything moves towards F electronegativity-wise. Which is more electronegative, oxygen or nitrogen? If you, oh, wait, hold on. I'm still trying to get used to this being able to add quizzes. So, which one is most electronegative? See, Alexa doesn't even know that one. Oxygen or nitrogen? It's oxygen. So, oxygen further to the right. So that means that we want the -1 charge to go with oxygen rather than nitrogen. Nitrogen can accept the -1 charge, but oxygen is much better at it because it's more electronegative. So that means that the most stable resonance structure is going to be A. The number 2 is going to be B, and the least stable is going to be C. So that's how we determine the stabilities of resonance structures, by using those 3 rules sequentially. And if you end up at rule number 3 and you still have a tie, then that means those 2 resonance structures contribute equally to the overall resonance hybrid. They have the same stabilities. Okay, so hopefully you're still with me. And now what we need to do is now we need to write the resonance hybrid. So what is the resonance hybrid? Well, the resonance hybrid is going to be the average of these 3 resonance structures. Now, the first thing you might say is, well, the average of these 3 resonance structures is going to be B. And that's going to be true, but what I'm going to say here is this, that because C is the least stable, it's going to have the least contribution to the overall resonance hybrid. And so what I'm going to do, what I typically will do is I will say, if you're going to write the resonance hybrid, only write the resonance hybrid for the 2 most stable resonance structures. Okay, and I have to tell you that, and so I will. So let's write the resonance hybrid for the 2 most stable resonance structures. And that we just determined was A and B. Okay, so how do we write the resonance hybrid? Well, step number 1 is going to be, let's draw the atoms in and just the single bonds. So my resonance hybrid is going to have an O single bonded to a carbon, single bonded to a nitrogen. Okay, in resonance hybrids, we don't worry about lone pairs. All I'm going to worry about are 2 things: bonds, charges. Okay, so now let's average the charges out. So on oxygen, we have a -1 charge here, and we have a 0 formal charge on B. What's the average? Well, in order for me to know mathematically what the average is, I would need to know how much more stable A is to B. And if there's one thing organic chemistry is not, it is not mathematical. So I don't care. Here's what I know. I know that oxygen has, that in the resonance hybrid, that oxygen is somewhere between 0 and -1. So let's represent that with a delta minus. What does delta mean in chemistry? Delta means partial. So that oxygen has a partial negative charge, somewhere between 0 and -1. What's its exact value? Don't care. Well, I will in a minute. The oxygen is slightly negative. How about the carbon? Carbon is and this is where I can use my big laser pointer. Carbon 0, 0, average 0. Nitrogen 0, -1. What's its average? Its average is delta minus. And the carbon 0, and typically I don't show zero formal charge or zero charges in either the resonance structures or the resonance hybrid. Okay, so now I've averaged charges. Now I need to average bonds. So in averaging the bonds, the carbon-oxygen single, carbon-oxygen double. What's the average of a single and a double bond? Again, what I would have to say is that it's somewhere between a single and a double bond. What's the exact value? Don't care. In order to answer that, I would need to know the difference in energy between A and B. I'm just going to say this. You know what? That's how I'm going to represent a bond that is between a single and a double bond, and I'm going to call that dotted line a partial double bond. So the carbon-oxygen is going to be a partial double bond. Okay, that's all I need to know. I just need to know that carbon-oxygen bond is somewhere between a single and a double bond. How about the carbon-nitrogen bond? Triple, double. What's the average? A partial triple bond. How do I represent that? With a dotted line with the triple bond. So I've got a partial double bond, and now I have a partial triple bond. Okay, so now this is the resonance hybrid. Whew. Okay, let's take a step back. What does it mean? Number one, this is the true structure. If I was to actually measure the bond lengths between carbon and oxygen, I would find that that CO bond in an OCN minus ion is somewhere mathematically between a single bond, which is longer, than a double bond, which is shorter. I would also find that the oxygen and nitrogen have negative charge. Now remember, the total sum here is -1. So the oxygen has some of that negative charge and the nitrogen has some of that negative charge. Who has more? Well, the most stable resonance structure was A, which means that the oxygen has more. This is going to have more negative charge, and the nitrogen is going to have less of the negative charge. But overall, they add up to -1. Why does the oxygen have more negative charge? Because it's more electronegative. So if I was to actually measure the charge on that oxygen, it would be higher than the nitrogen. But they both add up to -1. Okay? So the resonance hybrid is the true structure. That's what I would physically determine the structure of. Okay? So this is how we evaluate and write resonance structures. And once we write the possible resonance structures, we have to determine their relative stability. And then typically if we have more than 2, I will eliminate the least stable and then just write the resonance hybrid of the top 2, of the most stable 2. And so the resonance structures, this is what, and I know a lot of you did this back in general chemistry. Maybe you did. It depends. Sometimes some professors hit this hard, some don't. It's been a long time since I taught general chemistry, but my first years in teaching, I taught both. And this was a subject that I hit pretty hard because I knew when I started with organic, this was going to be something that we reviewed. So resonance structures are going to be important, and this is how we draw them, this is how we evaluate them, and this is how we write the resonance hybrid. Okay. There is going to be an online quiz for you to write out the resonance structures and resonance hybrid on paper and then upload that into Canvas for grading. That's going to be an online quiz. And I believe that you could do that with NO2 minus, or you could do that even with this phosphorus. With the PO4, you could also, well, actually, you can't do that because it's symmetrical. But there are other examples in the practice problems that you can draw Lewis dot structures for. Okay, so take a step back. What have we talked about? We've talked about Lewis dot structures to resonance structures to evaluating resonance structures. Along the way, formal charges are important in that. Now, in your general chemistry class, that might have been 2 weeks, 3 weeks. That's been an hour. So again, this is why we're reviewing this, because we're going to put this in the organic context as we go along. Okay. Now, also in general chemistry, after you talked about Lewis dot structures, you then moved into different types of formulas. I'm going to briefly introduce this. This is going to become commonplace very quickly. Drawing different types of formulas and particularly organic formulas. So just so we have our terminology correct, a molecular formula is one that gives you the total number of atoms in each molecule. So for instance, if I had that molecule of methanol that I had before was a carbon with 4 hydrogens and an oxygen, that's a molecular formula. And I might write that formula, if you remember correctly. The first one that I started with looked like this in terms of its Lewis dot structure. I might also combine these together to call that a CH3 group and then have it attached to an OH. And I'll get to that in a minute. But the molecular formula tells you exactly how many atoms are in that molecule. An empirical formula would give you the simplest ratio of the atoms in a molecule. So, for instance, if I had a hydrogen attached to a carbon that was in a triple bond, this molecule is called acetylene. We'll talk about this in one of the upcoming lectures. So acetylene would have a molecular formula of C2H2, but you could write its empirical formula as C1H. So in other words, you divide through by the lowest common denominator. So that just gives you the simplest ratio. And then the structural formula would actually give you the connectivity as a Lewis dot structure. So both this structure is a Lewis dot structure, a structural formula, and this is also a structural formula for acetylene. Now in organic chemistry, what we're going to do is we're going to sort of build and have line bond structures as well as some other types of structures. So let me just kind of outline this, and you'll get better at this as we go along. So here's the molecule ethanol, which is grain alcohol. Ethanol is C2H6O. If I wrote out its structure, I would have carbons here. So this is my carbon with 3 hydrogens, carbon with 2 hydrogens, the carbon-carbon bond, and then a carbon-oxygen bond of the OH group. Now, what I can do with this Lewis dot structure is these get really tiring after a while for organic molecules. And so what I usually do is I usually will take the atoms that are attached to each carbon and I'll kind of combine those together. So this is a carbon with 3 H's. So it could be written CH3, or I suppose it could be written H3C. Then this group right here is a CH2 group. And then usually I will write all non-carbon atoms. I'll put those individually. And so this becomes then a CH3 attached to a CH2 attached to an OH. So you can write this structure out, In the old days when we had to type everything out, that was what is called a condensed structure. And what we will typically do in this class is write what is called a line bond structure. And the reality is we'll actually use a combination of line bond structures and condensed structures. So what a line bond structure is everywhere there's an intersection of a line, that's a carbon atom. And every end of the line is a carbon atom. Unless it's not, and you write an oxygen or a nitrogen there. If you're going to convert a line bond structure into a Lewis dot structure or even a condensed structure, what you do is you just simply put the carbons in the intersections and end of lines, and then you add enough hydrogens to get you 4 and only 4 bonds. Hydrogens give us 4 bonds. Now, let me take an aside here for a moment. Biggest mistakes you can make in organic chemistry. I have 3, and it's like state law. I have to give you these in a lecture. Number 1 mistake that you is taking the class to begin with, but you don't have a choice, so okay. Number 2, 5 bonds to a carbon. Carbon cannot form an expanded octet, so only 4 bonds to a carbon. We'll get to number 3 later on. If I could get to 10, I could sell a t-shirt. But in 25 years, I've never gotten to number 10. Anyway, digress. Back to this. So end of line, intersection of line, carbons, add enough hydrogens to give you 4, and only 4 bonds. Okay, so that's how we draw our line bond structures and how we can convert them back and forth. You'll get better at this as we go along. Okay, so now where we're at is the following. We are at the next step that you learned in general chemistry. You went from Lewis dot structure to resonance structures to then molecular geometry. So the 3D structures of molecules are exceptionally important, particularly in organic chemistry, and we'll see that next in the next set of lectures. How do you get the 3-dimensional structure of molecules? You get them by getting the 3-dimensional structure of the atoms that make up the molecular structure. So how do we determine shape? The shape is going to be given by the number of valence electrons. And remember, what are the valence electrons? The valence electrons are the outermost electrons. That's what we've been writing when we've been doing Lewis dot structures, if that hasn't quite hit you yet. Great. What do we use? We use VSEPR theory, valence shell electron pair repulsion. So first, we need a correct Lewis dot structure. Then I'm going to convert that Lewis dot structure to a geometry. So here is the slide I like to show electron pair geometries. Now, there's a difference between electron pair geometry and molecular geometry. And we're going to deal with electron pair geometry, and I'll explain the difference in a few minutes. But remember, the whole idea here is that these electrons that are holding the atoms together as single bonds are balloons of negative charge. And since they are big clouds, big balloons of negative charge, they're going to repel each other. And what valence shell electron pair repulsion is repulsion. They're trying to get as far away from each other as possible. So when you have 2 pairs of electrons, or in terms of maybe having 2 single bonds, they're going to be 180 degrees away from each other. We call that linear. When you have 3 clouds or 3 single bonds, they will adopt a trigonal planar geometry. Because again, these negative clouds of negative charge try and get as far away from each other as possible. When you have 4, which is the most important for carbon, you have tetrahedra. You have a tetrahedron. When you have 5, you actually end up with what's called trigonal bipyramidal. And trigonal bipyramidal has 2 different positions. You can think of this as a combination of linear and trigonal planar, which is what they did in these balloons. So you have what we'll call axial positions and equatorial, and we'll talk about those later on. And then when you get to 6 clouds of electron density around a central atom, you end up with an octahedral geometry. And we have an octahedral geometry. Okay, so we have these 5 basic VSEPR geometries that we're going to work with. And what we're going to do is fit lone pairs into these geometries as well. Okay, so this is the basics of VSEPR theory. So what are our guidelines for writing VSEPR structures? Well, number 1, you need a correct Lewis dot structure, and you need to show all the electron pairs around the central atom. And for the most part, we're going to be working with the central atom. Then what you're going to do is count up the number of electron pairs. So let's take, for instance, water. We'll do something easy. So water has that Lewis dot structure. I mean, hopefully you can write water from general chemistry. May take a little bit of review, but there's our Lewis dot structure for water. So when I'm looking at what is the geometry around that oxygen, what I'm going to do is I count up the total number of electron pairs, and I'm going to include in these electron pairs, I'm going to include both the bonding and the non-bonding electrons. So in this case, I have 2 bonding pairs and 2 non-bonding pairs, right? So I have my 2 bonding pairs, my 2 non-bonding pairs, which means I have a grand total of 4 pairs of electrons. So the other thing we do is we treat a double and triple bond as if it was a single electron pair. We'll get to the reasoning for that in the next video where we deal with hybridization. Okay, so here is our next step, which is we use the tables before to predict what the basic geometry will be. 4 electron pairs means that the oxygen will have a tetrahedral geometry. Now, what am I doing with these bold and dashed thingies? Well, those thingies are called wedges. So the way we represent a tetrahedron, a 3-dimensional structure in a 2-dimensional space, is all bonds that are normal are in the plane of the paper or the screen. The wedges that are dashed are behind the plane, and those that are bold are in front of the plane. So that's how we represent a tetrahedron, a 3-dimensional structure in a 2-dimensional space, like a plane, a piece of paper, or the screen. So our oxygen then is tetrahedral. There's going to be lone pairs on 2 of those positions and the hydrogen on the other 2. Does it matter which ones? No, it doesn't matter which ones. So oxygen has what I call a tetrahedral electron pair geometry. Now, for those of you saying, but in general chemistry we called it bent. Okay. Bent is a molecular geometry. So if I was to just look at water molecule, I would not see the lone pairs. And so in terms of water, it has a molecular geometry where we ignore the lone pairs of being bent. I'm just going to use electron pair geometry because I want to see the electron pairs. So the bent, the pyramidal, T-shaped, seesaw, we're not really going to deal with. We're just going to deal with the 5 that were on the previous slide. Okay? So that's what we're going to look at. So water, oxygen is tetrahedral. Okay. If we're looking at bond angles, this is where we look at the basic bond angles. For a tetrahedron, the baseline is 109.5. In general chemistry, what you found was that because lone pairs are unconstricted by the bond, they're huge clouds. And so those clouds tend to push or repel the other clouds so that it squeezes the bond angles down from 109.5 to 107 in ammonia, which is NH3. And these two lone pairs of the oxygen try and get as far away from each other as possible, and they squeeze the hydrogens together so that water has 104.5 bond angle. So I'm not necessarily concerned about that too much in organic, but that's where this all fit in general chemistry. The idea that the lone pairs are just basically huger clouds of electron density, and so they repel each other and squish the other bonds together. Okay. And so that's just another view of that.